last time we discussed association rules, we started discussing association rules, and it was all about finding rules like implications like these ones, which basically predict the presence in a transaction of an item, like in the first one that's milk, based on the presence of other items in the same transaction. And so the two measures we used were confidence and support. Support meant how frequent were all the items inside the rule present inside the database, and you can have it support between 0 and 1, which is the percentage inside the database, or just the raw count, and confidence, which basically was the conditional probability of the second item, the item like milk, so the tail of the rule be there when the head of the rule was present in the transaction. So the interesting part was that basically given one item set, one set of items like bread, jam, and milk, you can actually derive a certain number of association rules. So you split up the mining process between first finding the present item sets, next finding the association rules. To find this, you could have used brute force, but the space was actually exponential in the number of items appearing inside the database. So given 100 items, you have 2 to the power of 100 possible subset count, check, frequent items to check. So the brute force is basically completely invisible, but actually you can actually note that if you have two sets of items, two item sets, x and y, if x is contained into y, then the support of x is greater or equal to the support of y. Okay? And this is basically this anti-monotone property of support is basically what gives birth to the a priori algorithm. And a priori algorithm is a level-wise search within the space of item sets. You start from the one item set, so the item set with one item. So up there you have A, B, C, D, E. And then you basically check them if they are frequent. If they are frequent, okay, you keep them. If they are frequent, you can actually eliminate all the items that contain one of the frequent items. So for instance, if AB, if two item set, so an item set of size 2 is infrequent, you basically can actually eliminate all the other items that contain B. So this is okay, but actually if you consider the level-wise search, when I say level-wise, basically means I do a query in the database asking to count how frequent is every combination. Okay? So even if I delete them, a lot of them, then I can delete a lot of them, then still every scan of the database can be very expensive. So that's something I don't like. Now, one possibility is, for instance, to change the representation and to have a very highly optimized representation. Instead of saying I'm going to keep the item sets and I'm going to count them, I'm going basically to associate not really the support to an item set, but actually I'm associating the set of transactions to each item and item set. Okay? So if I have a vertical representation of the database, this one, the interesting part with respect to the other representation is that, for instance, if I want to know the support of AB, I can just do the intersection of the two sets. So if I have a highly optimized structure, data structure for this operation, then I'm really, really fast in this. Okay? And as I told you last time, if you remember something about C, if you use assigning to represent sets, okay, that operation can be really, really fast. Now, what is still bad about this is that, well, vertical representation has some advantages, but what if you can actually do one scan of the database, actually two scans of the database, and basically then work everything in memory, and And then what happens is you are not generating any more candidates, you are not doing the tree in the traditional sense, you are not considering all the possible item sets and all the possible combinations, but you are doing something completely different. Okay? And so basically what came out was the frequent pattern tree structure. Okay? And the idea is that you can take again the same transactional database, do a first count, and you count all the item sets, the one item set, so A, B, C, D, E in this case. You count how frequent they are, and then you resort every transaction in, so that the most frequent one appears at the beginning, the second most frequent one at the second place, etc., etc. Okay? So the original transaction there was A, B, D, E. Now it's B, E, A, D, because B is the most frequent one inside the database. E is the second most frequent one with respect to the transaction. A comes next, and D comes next. Now, what you can do there is that you take this representation, and what you build up is what is called the frequent pattern tree. For every transaction, you start from a node that is the empty node, okay, our root node, and you start basically inserting inside the tree every transaction. Okay, so at the end you obtain these three. Obviously, when you do this, you already eliminated all the possible infrequent items of size 1, because that would be completely useless. Okay, you're not considering them. Okay. Now you consider these three, and actually this tree is actually a representation of this. As I told you, if you check out another very famous book in Yawei Han's book on this type of structure here, there is a table that connects every item to basically allows you to traverse the tree to connect every item. So for C, I have a connection here, here, and here. So I can traverse the tree and I can count how many times C is present, etc., etc. But this is a simplified view of the. Now, from this, that represents basically all the transactions, I start from the bottom, and I start to say, okay, I'm going to try to find the conditional frequent pattern tree, and I start with the ones that ends with D. So what I'm going to say, I want D is the least frequent one because it appears at the end, obviously. And now I'm going to find all the prefixes that basically end up in D. And so these are my frequent item sets that ends with D. Now, if I did the ones with D, then I move forward, and basically D I cannot consider anymore. What is next up to the tree is C, and do the same. And then on that tree I do E, and I do the same, and then I end up with B, which is the last one. Okay? And these are the conditional FP trees derived. How do you derive the one for D, like we did last time? And these are all the conditional FP trees taken from the example in your textbook. One of the things that is interesting in all these algorithms, and this is completely different than in other cases, all these algorithms basically keep the complete representation of the data, both the FP tree, both the CLAD, both a priori. So they preserve the complete information about the content of your database. Actually, FP trees are very nice because actually they put everything in memory and they can work in memory in a very compact representation. So That's something like that is really, really good. So they are not complete in common. Okay? Why FPGRO is one of the best algorithms around? It doesn't generate the candidates. Even a cloud that generates the candidate. It generates the candidate in a very easy way to counter their support, but still it generates the candidate. This one doesn't generate the candidate. Doesn't generate the candidates. Okay? So it avoids one basic step that is the most expensive step overall. Okay? And that's, as I said, together with, it's not an approximate algorithm, so you have the same, you have the complete representation. It's actually very compact. You skip a very expensive step, so it's actually very, very good. Okay. Now that you have the item sets, you need to generate the rules. Okay. And rule generation actually is kind of in principle working exactly like the part of the item set. Okay. Now, suppose what we said, why we were working on the item set, because we said, okay, if we have A, B, C, D as an item set, as a frequent item set, from A, B, C, D, we can generate several rules, right? This one is frequent, so I'm okay, and so I can actually start generating all the possible rules from here. Well, there is a standard rule that is basically this arrow empty, which we're not interested, and empty arrow this, which I'm not interested, but then there are all the other ones. Okay, all the combinations. Like. Now again, if I have a k element here, I have 2 to the power of 2 to the power of k minus 2 possible rules to generate. But what is interesting is that I find some property that is actually very similar to the one that is used for a priori. And just to explain this, is actually if you have 2 rules, right, and you are basically right now support is okay. So support is the given fact. Support, everything you are dealing with as enough support, as a larger support, as a support large enough. But if I do something like this, if I consider this rule and I consider this rule, and I compare the confidence of this, I can actually note that the confidence of this is higher than the confidence of this. Okay, so it's put it in very simple way. It's actually easier to predict one item than more items together, right? So basically, it's actually a very similar property that allows us to prune the space of rules, because actually I start with the top rule that is not really interesting, but I take one item set. I consider the item set, the rules generated by just having one item on the tail. Okay. If the confidence is too low, there is no way I can have a larger confidence with more elements on the tail of the rule. So I can actually prune down everything there. Okay. So it's actually very powerful in this sense. Okay. And so, for instance, this is how you generate rules. Okay. And this is an example taken from your textbook, which is basically, if you run the previous example we've seen, those are the item set that comes out, and that's the item sets. And so these are some of the rules you can generate. Okay? This is the running example in your textbook. We're going to revisit it maybe when we do some exercise from written exams. Any questions so far? Now, the question is, it's okay, support and confidence are okay, but actually they're quite limited in some sense. Okay, support gives me the how often some items are inside my database. Some set of items are inside my database. The confidence kind of allows me to say how much the presence of some items is predictable, but still is something relative to the database. So depending on the on how the items were bought, for instance, a confidence or a support of 0.01 might be an interesting value or not. So suppose that I take something like Amazon's selling patterns, okay? And imagine that everybody of us actually has a big string of 0 and 1s, whether they bought or didn't buy or didn't buy, bought or didn't buy something from Amazon, okay? Now, the point here is that, for instance, given the number of items in Amazon, the number of customers in Amazon, etc., given that, for instance, one item was bought by the 0.1% of the first people, or the customers, it might be a very good threshold for support. At the same time, if I say, oh, you know what, okay, let's do it at the Politecnico and let's consider the exams at the Politecnico, and say, you know, this exam was taken by 0.1% of the students. 0.1% of the students at the Politecnico, especially, say, computer science is one of the largest faculty, is still basically nobody, okay? So, depending on your data set, depending on some of the buying patterns, depending on the application, it might be really difficult to set up what is a nice support and confidence measures. So at some point they came out with different ways to measure the relevance of the rule, okay? Independently from there, okay? And obviously, you know, sometimes if you set up, if you make it wrong and you set up your, for instance, your minimum support to low, you basically maybe come up with a brute force approach, okay? For instance, at Politecnico, if I say a min support of 0.1, I basically take everybody, because 0.1% of the students at the Politecnico of computer science, maybe it's less than one student, really. Okay, so it's actually something that's really, really, really low. So basically, if I take the min support to low, it's basically making it as a brute force approach. If I take it to high, basically I look at the trivial stuff. Okay, if I ask us about something like a pattern in your CV, in your curriculum, that is basically present at 80%, probably I'm taking all the exams that are mandatory, like formal languages and compilers and databases and stuff like this. So it's trivial, okay, as an association. So what they came out was something that could try to measure the fact that would be interesting, because it was kind of surprising. First measure is lift, and actually if you check out the notebook I gave you about association rules, it's actually they just print the lift immediately. You're not asking please print me lift, but actually they just right away print lift as a measure together with the support and confidence. And lift for the rule is actually shown here. So if the two item sets are made of independent items, okay, so that lift becomes 1. So 1 basically means I should expect that, okay? So what I'm looking for when I print the association rules is something that is really surprising inside the database. And so I'm taking for this value much larger than 1, okay? So this is the number of times, the percentage of time they both appears together, okay? So if you consider them, please allow me to do this, to say this. Do you consider this some kind of events? The events that X and Y happen together, okay? Over the probability of X times the probability of Y, if this is 1. So basically they are independent. But if it's much larger than 1, something that shouldn't, You know, I was not expecting, given the distribution in the data of the data inside the database. So I'm looking for something like this. Okay, and so I'm very happy with something that is a very high lift. There's been other measures. I'm not sure that in the library that I pointed you inside the notebook is present, but you have an average, which is another one. So it's, as I said, is the difference between the observed and expected joint probabilities. So it takes more or less the same measures, okay? And so somehow instead of making the ratio of these two, it's basically making the difference, okay? And so it tries to give something that is an absolute measure of how surprising the rules are. But there are several other measures that have been developed, okay? But they basically leave this most famous one, for instance. And leverage, if you check it out, as a formula, is actually very similar, but it gives the raw difference, okay? Now, this comes out to evaluate, because actually consider this, when you try to do associational mining, you might come out with thousands of rules, okay? And somehow you have to understand what you should present, what is interesting for you. So, first, you have to kind of have the possibility to sort the rules and say, okay, the top 10 are the best one, and this I can show to the client, and so I'm happy. Now, the problem also is that, for instance, you might have several item sets that are related, okay? Because suppose if A, B, C, D is very frequent, then all the subsets are frequent, okay? So does it make sense to me that I go to a client and I say, you know, this combination is very frequent, and I give all the combinations? Because if A, B, C, D is frequent, then A is frequent, B is frequent, C is frequent, D is frequent, all the combination of these, all the three combination of these, etc. So what they came out with, it's a set of definitions that would allow you to summarize this immense quantity of item sets with a few exemplar item sets. Okay, so that was the entire idea. I can come out with something that is thousands of rules or thousands of item sets, but actually I can summarize the entire result in with very few notions. Okay, and so these are the main concepts. So somehow you have, for instance, the maximal frequent item set. So, and what you're looking for that item set that has no superset that is also frequent. Okay. It's kind of, if you consider the tree, some kind of the border of the search, okay? Because, well, I will show you later, but if you consider the search tree, a priori tree, basically maximal item set tells you that you started from your empty node, you're right here, and this is maximal, you didn't continue afterwards, okay? Because there was no superset that was frequent, okay? So somehow it gives you the border of this. And the idea is very simple. Technically speaking, suppose that I have this immense tree that is being developed. Technically speaking, everything that was contained here is still frequent, okay? So I can either print all this stuff and give it to a customer, or I can say, this is the maximal stuff, the maximal item set, maximal item set. So anything that is contained here, any combination of what is contained here, for me, is still maximal. So, as I said, it's a condensed representation of what you're looking for, okay? Now, what you define, you have, okay, one of the things is that, for instance, there is a notion here between maximal frequent item set and what comes next, is that when I gave you this, you actually cannot understand what is the support of what I contain here. I tell you that below this, there is nothing, but actually, I cannot give you some indication of what is of what is the value. Okay. So, for instance, if you consider the closed frequent items, what you have is that I'm telling you that if you go below this, the support is strictly smaller. Okay? So, the support here, you remember that the support is higher here. Now, the support here, everything that goes below is strictly smaller than this. Okay? Now, what tells you, what tells this is that if you know the support here, you know that everything that goes below here is going to be smaller. So it gives you an indication. You are here, and everything that goes there is actually strictly slower. Something that you cannot say with maximal stuff, because everything here will have almost the same support. And then you have the minimal generator, so that's minimal generator says this is the closed. Okay, these are the closed one. The minimal generator says that everything goes up. Okay, they are strictly higher. So, as I told you before, the three elements together try to tell you where is the border and where below there is nothing. But even here, I can say something about what's up. So, if this is a generator, everything up is strictly higher. If this is a closed one, everything below is strictly smaller. Okay? So, somehow they try to find measures that could identify something that is really interesting, okay, as a compact representation. So, if you go back to our data set that is taken from your textbook, and those are the items that we generated. So, now, this one here, okay, let's say. Now, if you consider this one, okay, the one with the maximal, the one with the shaded one with the double border are actually the border. Below here, there is nothing, right? So if you remember this picture here, I take this one here, and everything that is contained inside this one is actually represented. But I can represent this by this. So, for instance, if I go to a client and I want to compactly present the results, instead of presenting all this stuff, I could say, you know what? For instance, I can show you that this is a frequent pattern, a buying pattern, or a frequent set of items that is appearing together, and all the combination of them are basically appearing together. And nothing that contains them is actually more frequent than this. Okay? Now, what happens here, for instance, ABE, okay, is actually not maximal because it's still ABDE, but ABDE has a much lower, a strictly lower support. So basically, it's a closed subset. It's a closed item set because it's here, okay? And actually, even DE is closed with respect to this. So somehow, if you check out the closed ones, they give you information about the inner part of the tree. Somehow. Sorry. Okay? Simple boxes are generators. So the generators tells you that basically everything above here is actually higher. Okay? So this is a generator because if I have fewer elements, or A or D, because the smaller one with respect to these are A or D, are actually have a strictly higher support. So above here, I can have something that is either 4 or 5. Okay, 4. That's 4. But actually, if you
see here is not a closed one because ABD is actually at the same port. Okay? You wonder why all this stuff came out, but actually if we generate the rules and if we try to generate the rules, you're going to see that even for a very small subset, consider here, we have only 6 transactions and 5 elements. We actually generated a reasonable number of item sets. Okay? And consider that from each item sets, you have a certain number of association rules that you can generate. So that's your issue. And somehow also, several times, you prefer to show, for instance, the item sets. Because I say, if I show an arrow, okay, and I say the association rule, what is an association rule is actually, I have to give some explanation, whereas to say, oh, people, I don't know, visit these pages together, okay, when somebody comes to your website, and this is actually one of the applications of the association rules, they see, they usually see, very frequently, see these pages all together, okay? So that's very, 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 very easy to explain to anybody, okay? Now, there is a very weird application, well, not weird, but peculiar application of frequent item sets, which is actually related to, I usually show this in, during the part of graph mining, but actually I wanted to anticipate this. And it's actually about the searching for small communities. Actually, this is taken from the book, from one of the textbooks, the one mining massive databases. Okay, this is part of graph mining actually. So, crawling is actually the search for small communities inside your graph. And so you are basically looking for different graphs where you have people discussing topics. So, or one community linking to another community in somehow. Okay? Typically is you have people that have enrolled inside the blog, okay, and there are threads, and then you want to know what people are talking about. Okay? And so you're looking for communities that discuss some particular stuff. Okay? So typically what you want to identify is this type of subgraphs. Okay? So what happens as a community, you're looking for KS, T, where you have basically subgraphs of this large community. Takes, for example, any big blogging site, okay? Like Reddit, you have users that discuss some threads, okay? I discuss some threads, but I don't discuss others, and somebody is like me, so I'm looking for these people because these people are a community that is interested, I don't know, in video games and data science, okay? Now, you're basically trying to look for a typical community that have at least S people that discuss T topic, okay? These are the 2 parameters of your problem. Now, this is really weird to think that this is can be modeled as an association rule mining, but you can actually do that. So, the idea is this. If I, as a person, I'm discussing, for instance, look, this one here. If me as a person, I'm discussing 4 topics, I see this fact as a transaction where there are the 4 topics. And I call this the Pieruca transaction, the height transaction. Okay? So there is a Pieruca transaction where I discuss 4 topics. There is a Loris transaction that discusses 3 topics, blah, 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 blah. Okay? So I model the fact that I'm discussing a certain number of topics as a list of topics, as an item set of topics, as a transaction. Okay? As a unit. Now, what you're looking for instance, when you're trying to identify some kind of community, if you think about this, if these are the transactions, okay, I'm looking for the frequent item sets because I'm looking for patterns of discussion that are frequent. maybe some other people like Pierluca is interested in discussing video games and data science. Okay? So these two are the item sets for me, and I want them to be frequent. Okay? So that's my my point. But then somehow I want also to have a lot of people discussing it. Okay? Because it's not if it's only frequent for few people, that's not really interesting. So I'm looking for instance, all the number of transactions, a certain number of transactions that is discussing this. So I'm looking for support. Okay, so that's how it's modeled. Okay, so somehow, if you consider, if I put a constraint of the number of topics I'm interested, is basically kind of the item set size. Okay, because this is the item set size. But at the same time, if I say at least the two people should discuss the same thing, that's actually the support of that rule. Because it basically means if two people are discussing data science and video games, it basically means that there are two transactions where data science and video games appear together. Okay? So what happens is that, for instance, there, I model every person, as any person, the giver, or any person which is basically identified with a small subgraph as the different transactions. Okay, this is a transaction, another transaction, another transaction, another transaction. There should be some dots there, but it's not. Okay, and so basically, for instance, I'm interested in knowing that, for instance, ABC, which is the tree pattern, has a certain support. Okay. That means that at least the value of support people are discussing these three topics. Okay? And so that's actually I would do that. Okay? So I take all the, for instance, I go online, I check out how Pierluca is behaving, I'm checking out where he basically actually answers some questions, okay, in a thread. Okay? Every thread becomes a part of an item set, and this becomes a transaction, the Pierluca transaction. Pierluca behaves like this, Loris behaves like this, Robert, if it's here, behaves like this, etc., etc., etc. Then I say, okay, I want, okay, I'm interested in knowing at least, I want to know a support of 10%, okay? 10% basically means at least the 10% of people is discussing some topics. And then if I put a constraint of the number of topics, I want to list at least having 3 item sets. Basically means 3 item sets with support 10%, basically means the people, okay. Let's look at this. The 3 topics were discussed by at least 10% of the people. Go, Loris. Is to find the community. Okay, is to find the community. Application is something like this. You have your own discussion all around. Okay, and then basically you say, okay, I put a support threshold of 2. So a support threshold of 2, it basically means 2 out of 6 nodes inside my plot, inside my graphs. 2 out of 6 are discussing something. Okay, there are topics that are being discussed by at least by 2 out of 6. Okay, so that's my goal. Now, if I do that, I found out that these are the frequent item sets. Okay. So, for instance, F is not discussing anything, right? Because F is actually I'm receiving only. This doesn't make the difference between topics and people right now. Okay, it's a simple example, but that's basically the connection you can have. It's basically C replied to F, D replied to F, but F maybe didn't didn't connect to anybody. Okay, so everybody against F. Okay. So the point here is that you take this, you basically say, okay, A is connected. It could be I'm friends with. I discuss this topic. Whatever I do. Okay. And so I take A, and A has an arrow to B. He has an arrow to D, and has an arrow to C. So it's B, C, D. So A is B, C, D. So this is my first item set. B, what is it? B is discussing only with D. So C is discussing with everybody. C is B, D, F, and A, but not A. So this is it. Now, if I say support, minimum support of 2, it basically means I'm looking for the items that has been discussed at least with the 2 people, that has been received answer, that has been received reply, that has been connected somehow inside my community with the list 2 out of 6. Okay? Now I say I take the support threshold 2 and I have these 2 elements. Okay? Now what do these identify? These are topics, correct? These are topics because these one, they were the ones that would appear here which received error. Okay? So I take B and D, I put it here, and I take all the nodes that were connected to this. And this is my first community I identified. Okay? I know that given what I have here, A, C, E were all replying to these things. Okay? To B and C. They were connected to B and C. The other one is ENF, which has support to ENF. I take ENF and I take all the nodes that connect to ENF. Okay? Because when I say that ENF is actually something that is frequent enough, it basically means that there have been enough transaction containing ENF. So it basically means there were enough people connected to ENF. Okay? And so this is the other one. Okay? So as you see, it's actually very peculiar one. What you do, going back to Glory's question, what you do with this is actually up to you. Okay? This is actually identified to sub-communities. Okay? And you can use it for anything that you can model with a connection somehow, where you identify some subparts of that entanglement of connections. Okay? It's actually pretty interesting, at least. I found it fascinating when I saw it because it was one of the most interesting applications for me of association rule mining. Now, when we talk about association rules, we talk about I bought milk, sugar, and bread. Okay? But then put it like, for instance, in movies. I bought, the 3 DVDs of the 9th season of the, what's the 9th season as? I mean, Walking Dead is 9th season or 7th season, whatever. So suppose the 10th season of Friends that I know. So I bought the entire collection of DVDs. Okay, and somehow in my transaction you might say he bought 1 and 2 and he has 3, or he bought 3 and 4, he has 5, etc. It could be interesting to know what was the sequence in which I bought. For instance, I can tell you that, for instance, you have visited the Politecnico or the Amazon website or my website, and you went, for instance, you visited, the exam page, I don't know, the software page, and I don't know, my publication page. Okay? It could be interesting to know what sequence did you use, especially if you are doing, for instance, and this was an application we did with Professor Cherry a long time ago. If you take the logs of the visits to your website, okay, and you check out the sequences that users do, you might try to optimize your website by saying, okay, if I see that you make some specific messages in your visits to my web page, I might decide to make some shortcut on the side, okay, and say, okay, depending on my analysis, these are the things that you typically want to see more often, and actually you make a lot of passages to do this, and I put the shortcut here. Or I might find out that, for instance, you usually go to my publication page, but as for how my website is organized, you're going to make 10 steps, 12 steps, 13, 15 steps. So somehow maybe I want to shorten that type of sequence. Okay? So what they did was to extend the concept of association rules to the sequences. Okay? Now, the idea, there are several extensions to this, because when you consider sequence, it's just not C happen after A and B, okay? But it would be also with time constraints, with several features, okay? We're going to see the basic ones. which basically says that A, B, arrow C means A, B happened before, next C. Okay, those are the subsequence. So when I search for a frequent item set, which was a frequent subsequence, will become, I mean that what I write first happened first, second happened second, third happened third. Okay, third position. And everything is about the order of the transaction. Think about anything that you can think of. For instance, there is an entire branch that is process mining that deals with the fact that you have procedure and processes defined inside the company, and then basically given their model of the software or their organization, that procedure is basically done in different ways in different moments, and you are looking for sequences, subsequences of how people can react or act inside the organization, for instance. Okay? But the easy way is something like buying patterns. I'm interested in knowing that if you bought, the first 2 seasons of the Walking Dead, probably you're going to buy the 3rd season, but in a month. Okay, something like this. Now the notation becomes a kind of awkward and a little bit more complex. So you have your sequence in the you have your sequences, so you basically consider the order, so you cannot do what we did with the frequent pattern mining, for instance. We have this sequence has an order, okay? And so when we define a subsequence, we say that basically it's a subsequence is a subset of the original elements, but that maintains the order, okay? So that's the thing. So basically you have your original sequence of k elements, okay? Now you have now some notation like a Python-like notation in your book that is basically S of I column j, basically means the subsequence from I plus 1 to j. This is your notation. But then if you have two sequences, S and R, then we say that R is a subsequence of S, and we denote it with the subset symbol. And so basically you are mapping the indexes of the subsequence R into the indexes of the subsequence S. It looks really complex here, but actually these examples are much easier. So suppose that this is a sequence A, C, D, G, A, A, C, G, okay? Then A1 is a subsequence of S, because actually I can map this position, I can map it to the second position, and then I don't care about the T, I can map the G here, and I can map A here, and I can map G here. So I basically don't care about A, T, and C, okay? Now CTGA is a consecutive subsequence because actually it basically takes a consecutive span of elements. And then you have the definition of prefix, which actually is what comes first, and suffix, which comes later at the end. Okay? So you take all these things to basically generate your measure of support. And so, for instance, if you have a subsequence, you say that the support of subsequence is the number of sequences in which that sequence is actually a subsequence. Okay, so the support of a sequence R is the number of sequences that is in your data where R was actually a subsequence. Okay, this is the support count, and in the book they call it relative support. Is actually the percentage. Okay, and the problem is actually the same. I'm actually looking for a value pattern, which is a temporal pattern, for which I have, for instance, a certain number of, a certain percentage. The subsequence appears for a certain, at least for a certain for which subsequence appears at least for a certain percentage of sequences. Okay. Now, what makes this difficult? The fact is that when I consider this operation, it's actually quite expensive. Generally speaking, I have to consider all the possible combinations of sequences inside a large sequence. Okay. Now, suppose that this is your database. It's taken from your textbook, from the chapter from your textbook. Then I have to say I can count how many times A appears, and A appears in all the three of them, G appears in all the three of them, E appears in all the three of them, AA appears in all the three of them. It appears as a sequence here, but it also appears as A and A here, and it also appears as AA here, skipping the C, and this is consecutive. Okay? And then you have all the stuff here. But how do you find this? You're basically doing the same approach you use with association rules. This is the basic algorithm. It's basically the extension of a priori to sequences. It's basically the same principle, and it's the simplest one. Okay, it's actually the simplest one. And so it works like this. This is the algorithm as you can see, but actually let's work like this. Now, you consider, for instance, you consider your data set, and you consider, for instance, here all the one sequences, okay? And you have the mean support of 3. Now, if you check out, so you want elements that appears in all the 3 sequences we have seen. Now, if you check out, C was not appearing in all the 3 sequences we had. So this one here is not frequent. So actually, we are not considering any subsequence that has C in it, because actually it would be frequent enough anyway. Okay? So from this part on is actually exactly as the first step is actually like a priori. Okay? The next thing is A is frequent. Okay? And now we consider all the combinations with the others. Okay? So AA we have to repeat because it would be the same. A and G and A and D. Okay? And for G, we consider that GA, GG, and we consider GT. Note that somehow, if we were in a priori association rule mining problem, this one here and this one here, they were considered equivalent. So there would be there were only one node like this, okay? Because AG and GA in association rules are actually the same. So we don't care about that. Here we care about the sequences. So basically our tree expands much more, okay? Then it's much more complex. Again, AT is not frequent enough, okay? GT is not frequent enough, so I don't think so. I don't use it. And T, for instance, anything that has another letter afterwards, one of the frequent ones, obviously, is actually not frequent enough, so I can eliminate that. And so here again, I say AA, I try to AAA, and try to AAG. Again, this one here, and this one here, or oops, 2A, 2G, so this one here and this one here are different, so they appear in 2 different places. So my tree is much bigger, and actually my count, the fact that I have to decide whether a sequence is frequent or not, my count of that support is actually much more complex. That's why these algorithms are much more complex, as you can imagine. Okay? And this is the algorithm. I only show you this. There are several extensions of the known algorithms to the case of sequences. Even the FP3 model and approach is actually present for them. Okay? Now, last but not least, for this, you can actually use association rules for classification. At some point in time, they basically said, okay, associations are really interesting, but think about this. What if I take an association rule and somehow I put a constraint on that? I said, okay, I'm looking for an association rule where, I think it's the case. You remember the weather data set? the weather data set, I showed it once, I think, but suppose that you have a data set for classification, okay? And you have your variables are outlook, temperature, humidity, wind, and then you have your attribute, which is the special attribute, which is place, okay? Now, typically this is a classification problem where your goal is to find a model that predicts whether you're going to play or not based on the outlook, which is sunny today, I would say, the temperature, the humidity, and the wind. Okay? So this is a classification problem. Now, again, an association rule is what does it do? It tries to predict the occurrence of the tail given the head. Okay, so in my basic goal in association rule is when I find this, I'm very likely to find this. And how much likely I'm going to find this is actually my confidence. Okay. Now, and this is based on the thing that you have, transactions, and you're looking for elements inside transactions. But at the same time, what you can do, you can say, you know what, stop. I'm not going to consider any possible C here, any possible Y here. I'm going to consider the class value. Now, if I'm going to consider the class value, I'm looking for something that says, when you find this, very often your class value will be this. Okay? So this makes this not really an association rule, but basically a classification model. Okay? And so that was what they generated with the idea to modify the existing association rule mining algorithm to focus the tail of the rule on the class. And so basically you are mapping an existing association rule mining algorithm in a classification algorithm. Okay? And so this is the CDA algorithm, which is one of them. And so, for instance, if this is the weather data set that I told you about, okay? Now, here we don't have transactions really, okay? We don't have transactions really. We don't have set of items really. But we can still generate something that is useful for an association rules. And so what we do typically, this is the result. What I do, I'm not really going back to this. If you consider the original way I showed a transaction database that could be used for association rule mining, it was something with the transaction and the transaction ID was 1, 2, 3, something. And here there was the items. Okay? And so here there was something like A, B, D, E, E, and then there was A, C. These were a set of items. So right now I have something that is a fixed notation with a fixed number of columns. So what happens is that most of the algorithms, actually all the algorithms who use this for association rules, they transform this in a set of attribute value pairs. So for instance, the first rule for me, the first row you see sunny, hot, high, false, no. Transaction-wise, if I consider this as a transaction database using association rule mining, it becomes something like this. it's basically equivalent to say Outlook is equal to Sunny, and this is one item. It becomes one atomic item, comma. And then my second item is temp is equal to hot. Then the next one is humidity. I just put the H is equal to high. And then you have wind is equal to false. And then the other part is, for instance, place equal to no. Now, this becomes for me atomic items like A, okay, or B, or C. And obviously, there is another item that could be Outlook is equal to Overcast, which is another item, okay? And so my rules are made of, my association rules are made like this, where if you check out Outlook is equal to Overcast, play is equal to yes, it's like, atomically, it's like A arrow B. Because this is my first atom of the information, the Outlook is equal to Overcast, and this one, play is equal to yes, is my atom, okay? And so if I have this one here, and play is equal to yes, is the other one, I'm basically generating item set where here I have the part that belongs to the attributes, and here I get only the items that belongs to the class. Okay? So that's how it goes. And actually we are not going to see classification rules. If you check out the slides from last year, and also the videos from the last year, there is a part on classification rules. We are not going to do them this year as in the slides. We are going to make, I'm going to show you some experiments like this, where I can show you how classification rules are like. They're actually very powerful in terms of explainability. So they're very powerful to show people, because if I show a model like this, it's actually much easier to show to people that knows nothing about data mining than showing a trick. Okay, so that's actually pretty interesting. No, not really here. If you do for continuous, Laura is asking, can we do it for continuous values? This model, if you want to have association rule mining, you have basically to discretize the continuous rule. So the continuous values, then you can, but that's tricky, and then we can discuss this when we do doing preprocessing. Discretization for you is like, I'm taking all your values of grades, and they are typically between 18 and 30 and loaded. And then I basically, maybe if I see the distribution of the values, I see that there is a huge, massive amount of people that took something between 18 and 22. And then there is a huge massive of people, huge group of people that took between 23 or 22.01 to something like at least 26, which is more or less probably the distribution, right? And then there are other subclasses like between 26, 28 and 28, 30, okay, for instance. And then instead of using all the range of data set, I remap these to 4 values, like low, medium, high, high, okay? And then I use those 4 values, and then I can use continuous values even in association rules, okay? So that's one of the points. Other question before we move on? Okay. We're going back with some notebooks next time about this, with this. For now, we step to something completely different. Which is clustering. Now, clustering is per se one of the most pattern to mine inside the data, for the simple reason that you can always apply clustering. I cannot always apply association rules. To apply association rules, I need transactions. If I don't need a unit of transaction, and the idea that there is a unit of information, and I'm looking for frequent association within those kind of units, like visiting my web page, buying patterns, whatever. If I don't have that, I just have information, I can do nothing much except doing clustering, okay? And actually clustering per se is actually very interesting because actually it's also considered a visualization technique per se, okay? If you consider back to the origin of EDA, exploratory data analysis, it was basically visualization, statistics, some statistics like summarization statistics plus clustering. And still today, if you check out some presentation and some courses about clustering, they say, oh, clustering is a very powerful way to basically visualize or explore the data. Okay? It gives you some information about the structure of the data. Okay? So it's actually, yes, some idea that it's actually a data mining technique, but also a kind of visualization technique. Now, the idea of clustering is very simple. The idea is to take some data and look for something that you call it natural group inside the data, natural grouping, where natural grouping is something that is intrinsic of the data. Okay? So I can say that intrinsically speaking, inside the data of there's a Lunga nearby here. If I check out the buying patterns, I can check out and I see people that, for instance, goes on Friday and Saturday and make a big shop for all the family, and I can actually recognize that by the buying patterns and the buy dates and buy time, etc., they're probably family. Okay, and then I can probably identify single people or students because they are completely different buying patterns. They don't go and spend 200 euros on Saturday because they have to feed the family the entire week, right? So basically that's present even if nobody tells me that. Probably if I check out and do clustering, if I look for grouping inside the buying pattern, probably I can find different buying patterns, okay? The same as if you go in Via Grosich, there is a Carrefour, you can get there and probably who's going there? Well, at lunch there is all people getting something very easy to take for the lunch. Or after 10, it's basically beer and others. And in the meantime, there are buying patterns of families, but they are smaller patterns because probably they are around the supermarket. Okay, because there are several supermarkets, so probably they are locals. Okay, so you can group that, you can actually identify probably some of the patterns, and you say intrinsically in the data I can see this. Okay, so typically you have some data. And you are looking, for instance, you're looking for images, and you are basically trying to group images, for instance, in some natural subsets. And what you want to find automatically, the dream is to do it everything automatically, is to have this set of images, having your clustering algorithm, turn on the engine, and then you find out as an output a number of groups, okay? So a number of clusters. And then, technically speaking, you would like the groups to be coherent. Okay, so the elements inside the group, inside the cluster, should be very similar to themselves. And on the other hand, if I take two groups, two distinct groups, they should be really similar between themselves. So that's basically everything about clustering. Okay, that's everything about clustering. Everything is around these two concepts. Give me the data, I find the groups, items inside the groups are very similar to themselves, but if I take two items in two different groups, they are very similar, okay? So, this, for instance, I run my algorithm and that basically groups the images like this, and I'm very happy, because actually I take the groups about the beaches, and actually if I compare the two images, they are very similar. And if I take the image of the beach and the image of the other cluster, the one with the green ones, the forests, actually the two images are very different. So I'm very happy. Okay. but at the same time, if something comes out like this, then I might be not that happy, because actually if I take something from this group, I take the forest from here, it's actually very dissimilar from the other ones, but actually it's very similar to the other group, so probably I should have gone the group together, so I'm not very happy about this. Okay, and I want to be happy. So, what is a good clustering? As I said, it's basically clustering per se. A clustering solution or a clustering is a group of clusters. Okay, and what I want to have high intra-cluster similarity. Inside the same cluster, I want to have a high similarity of the items, and low inter-class similarity. If I take elements in two groups, they should have a very low similarity. Okay. Now, how do I do this? Well, first of all, I use similarity way too many times, and we have to define what is similarity. And this is actually really, really difficult. So everything rotates about the fact that you can actually generate an interesting similarity function. Okay? For instance, well, we're going back to that, but for instance, similarity between words, and similarity between images, and similarity between other stuff, it's actually a really massive problem. Actually, for similarity between words, for instance, one of the great breakthrough was by deep learning. Okay, so for instance, something that we're going to see when we're going to talk about text will use something that was developed inside the deep learning community as a solution. Okay. Now, I have similarity. I want to have a very good similarity function. And at the same time, I say, okay, if I know what is similar and what it means to be similar, how can I use this to create the groups? So there are the 2 points, okay? And this basically influences the quality, the final quality. Now, finally, so I say, okay, I have the similarity function, I have my algorithm that produces something. How can I evaluate this? Okay, how can I evaluate this against this? Okay. Now there are several ways to evaluate that. Evaluation of clustering is actually one of the definition of the similarity and the evaluation of the results is actually the critical part in clustering. Okay. And so I can actually have a very different way to evaluate. For instance, here I can actually run something that if I have a good similarity function to evaluate the result of this, I can actually run the similarity function and say, you know what, actually I can find 2 elements that are more similar but belongs to different clusters, so it's really weird, the result, which is okay. But at the same time, suppose that I make a real application. I go to Mr. Esselunga or Mr. Carrefour. They give me the data. I basically do the clustering of their data. I generate my clusters. I have to present to them the clusters, and I have to convince them, okay, that they are okay. So now, no clients will basically be happy just with the measure of coherence of separation of clusters. They want to have something that is, actionable per se and that you can understand. So maybe you have to do a manual inspection. You show the single patterns, or you somehow come up with a way to show what's inside the cluster, and actually you have people, experts, manually inspecting what you show as a result of the cluster. Okay, so that's what you do, what you can do. Okay. The other way around, you can actually benchmark on existing labels. Okay, you can actually use Mr. Esselunga already as the label for who are families and who are students, because typically maybe they have on the card the loyalty card, or they have other things. So you go there with your own prediction of what are the clusters, and they say, oh, okay, you did not know who were registered as family or as single guys or single people. So what you have, we compare what you give us with what we know. We compare it and we can measure. Okay, so these are the 3 approaches. You check out somehow the structure and you are happy. You check out with the manual inspection with an expert, or otherwise you have a criteria, control criteria to check it. Okay. As I said, clustering is a collection of clusters, a cluster is a collection of items, and ideally you have a program, you push a button, and automatically it turns out with a set of clusters and the measure of evaluation. Okay, so that's your idea. As I said, the applications are many. Actually, since you can always use it, basically you can apply to everything. The point is, what are the results that are being produced? Okay. So, for instance, I can actually, if I want to see how much green is there inside, what is the largest or what is the distribution of green areas around Milan? Okay. I take the Google image of Milan, and what I'm looking for pixels that are kind of green that are nearby. Okay. So similar points. So my data points are pixels, and my similar points are not just green pixels, because I'm not happy if you have a pixel here, a pixel there, everywhere, but I want to look for the big areas. So for my similarity measure, I say that the items are similar if they are nearby. Okay, if the pixels are nearby, they have the same color. So my groups are going to be groups of pixels of the same color. And for instance, I'm looking for the green ones. And so my clusters shows area of Milan with a similar terrain of complexity. Like if they are all greens, probably they are kind of green and others. If they are all gray, probably they are roads, etc., etc. Okay, I can do that. I can take this night sky and, for instance, look for stars, to count the stars. I apply clustering, I eliminate the black ones. I take the white, just the white color, and then if I use clustering, I can come out with the clusters of white pixels that are nearby, and I can actually count the stars. Okay, I can do several things. In marketing, segmentation is actually typical, very typical things. You give me some customers, you give me their buying patterns, I try to find a group of customers with the same similar buying patterns. Insurance almost the same, okay? If you have risk and actually you have insurance that you've been paid or incident, I can actually group incident report to accident report to basically find accident patterns that are typically and similar, okay? To find, for instance, a group of people that should have the same type of insurance, okay? As I said, you can have anything, okay? Now, as I said, how do you measure the quality though? Well, basically, first of all, you have you need to have a similarity measure. Typically, similarity measure is mapped into the context of a distance, okay? I have a data point and another data point. I can actually say I build a similarity function that is very high if the point is the same, okay? Or I can say it's a distance measure, which is very low if the similarity is very high, okay? So you can actually say, you actually will hear me using the same interchangeably distance and similarity. When I say distance very low, similarity very high, okay? We're going to see an example of this. Typically, given the similarity function, you might have also a different measure that use this similarity function to measure, to estimate the quality of the final product you have. Okay? Now, similarity is actually really tricky because similarity can be very easy to, in some sense, in some variables, and it's very difficult in others. So, what does it mean to have similar eye color? Okay, if we register the eye color with a string, so it's categorical, it's actually either blue, brown, green, gray, suppose. What I can do is actually either you have the same eye color, so the distance is 0 or the similarity is 1, or you have different eye color. That's it. I cannot do much more than that. If I measure height, as we did the last time, I can actually have a measure that is kind of different. Okay, but then, for instance, how do I measure the difference between, for instance, in a data set where I have the income, as an example that I usually use, I have the income as a variable and the age as a variable. Okay? What can I do? Well, I could use, for instance, okay, Euclidean distance, but then it's still tricky, because if I use the Euclidean distance, and in one variable is age, one variable is income, and I have, I don't know, 2 people here, and I use this as, distance as a function of the similarity. My problem, for instance, here, even if it's actually very nice to have something that is numerical, so it's Euclidean distance is perfect, but for instance, income has a larger scale than the other one. So probably I have to normalize this. Okay. So as I said, it is tricky. Actually, for instance, if you ever see, suppose you are in a company, a data scientist like me comes to you and says, okay, I built the segmentation of your customer base. It was all numerical, I'm doing the clustering, blah, blah, blah. It was amazing data, and I found these groups. These groups are amazing. This is my result. Oh my, you're going to see my within sum square has been minimized, my between sum square, blah, 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 measures, plots, and stuff like this. First question you should ask is, what similarity measure did you use? Okay? Typically, most of the people, since by default they use by default, if you run any algorithm is Euclidean, they basically have Euclidean distance. Okay, but that's okay. Since similarity basically influences the entire result of your process, you should really know what is underlying your process. That's the first question. Now there are hundreds, if not thousands, of clustering methods. We are going to see 4, 5. They divide themselves because they are basically, sometimes they are hierarchical, in the sense that they don't produce a clustering, they produce a hierarchy inside the data. So they don't produce just a solution, but they produce a hierarchy of solution. They can be numeric or can be with symbolic data. They can be deterministic, like I'm a good customer, I'm a family guy, and my pattern is inside the family group. Or it could be probabilistic, like Pieruca has a pattern that is 80% probability to be in the family group, 20% probability about a single guy. It could be exclusive overlapping, which is kind of connected to deterministic or probabilistic. You can assign me to one group, like Apple buyers, okay, the Apple users, but you can also assign me to Apple users and Linux users, okay? It could be hierarchical, flat, top-down, and bottom-up. There are 2 structures that you are going to use. First of all is the data matrix, so the data, except file of C. The other thing that is used typically is going to be the distance matrix. Distance matrix, you recognize it because on the diagonal it has 0. If in any book or in any text you find something that in the diagonal is 1, it's basically a similarity matrix, okay, which is actually basically the same, okay? Similarity is maximum in the diagonal because every element is similar to itself in the maximum. Okay? Since we have to go through the similarity measure, we stop here, and I see you on Wednesday. Okay? Have a great weekend.